As Charlie said, my name is Kurt Lloyd. I'm a NASA software engineer. And as he said, I work at the Kennedy Space Center here in Florida. And what I'm going to talk to you today about is living off the land on the moon and on Mars. And some of this will sound a little bit familiar from our previous speakers. Let's make sure let's see this, if this works. I'm trying to click and nothing's happening. Is my cursor on? Make sure the cursor is like in the middle of the screen. It's probably necessary. There we go. All right, technology is working. That's a good thing. Every year in history classrooms all across the United States, young students are taught about the great westward expansion by the early American pioneers. These visionary pioneers were drawn to the ideas of exploration and adventure, along with the promise of a land of opportunity that was now open to them. They were inspired by the prospect of wealth, by stories of vast resources that were free for the taking. They dreamed of a fresh new start and a better life for themselves and for their families. Things were not always easy for the early American pioneers, though. They faced danger and even death in their efforts to conquer this new frontier. The harsh and unpredictable weather was one of the biggest dangers. Winter often brought terrible blizzards, killing both people and the animals they depended on. They also encountered dangerous wild animals like the large and powerful grizzly bear. And if all that wasn't dangerous enough, the American explorers and pioneers also had to deal with some pretty nasty diseases. And these folks seldom had any real medical expertise, so even a bad cold or the flu could sometimes claim someone's life under these circumstances. My point is that this was not an easy task. These explorers didn't know if they would even make it when they set off on their journey. They took a lot of risks. But now, in hindsight, we know that it was worth doing. The payoff was really great for them and for the future of the entire country. Can you imagine the logistics required for a trip like this? Although these pioneers and settlers did pack up a bunch of supplies onto their horses and their wagons, these cross-country journeys lasted 4 to 6 months, or even longer if they ran into trouble. So they were prepared to live off the land and use the local resources in order to survive. The early American pioneers had some pretty compelling reasons for their exploration. But why do we feel the need to explore outer space, asteroids, and other planets? I love a quote from William Pomeranz, who's a real visionary in the space business. He said, "Our universe is enormous. It's mind-bogglingly big and diverse, and our reasons for going there are correspondingly large." He said this after showing the audience the Hubble Ultra Deep Field image, which is a single Hubble Space Telescope image that covers only about a thumbnail's worth of dark sky. But that image contains about 10,000 teeny tiny galaxies. So his point was well taken. Here are just a few of the mind-bogglingly big and diverse reasons for going there. Probably the biggest reason is the technological return. Just about every time NASA takes on a new mission, it has to invent new technologies, or at least advance existing technologies. Entire industries have been built on space technology, including personal computers and natural resource mapping. This is a picture of 13-year-old me playing on my Apple IIe personal computer. I really loved that thing. I still have it, it still works. In this photo, I'm playing a game, but I didn't just used this computer to play games. This computer taught me how to program, and it helped mold me into the NASA software engineer I am today. I might not have become an engineer if it weren't for this computer. I might not have ever worked for NASA if it weren't for this computer. We're all influenced and molded by lots and lots of people and by lots and lots of experiences growing up. But I honestly believe that this computer played an important role. And I don't believe this computer would have ever been invented if it weren't for the space program pushing that technology and miniaturizing it for space. My cursor may have moved because it's not going to the next slide. Make sure the PowerPoint is in focus instead of the, there we go, thank you. Another reason for exploring outer space is the scientific return. Space exploration almost always leads to new discoveries, and it leads to us learning new information about our world and about our universe. It expands our human knowledge, and it can completely change our perspective. Sometimes this new information changes our perspective of our own planet. It can show us our own planet's fragility and smallness. It can give us new respect for our planet and for our neighbors. It often helps us be more safe and be more prepared from weather disasters, for example, or from other big scary things like large asteroids on a collision course. Those are all pretty great reasons to explore outer space, but there's also a huge educational return. Space exploration can inspire future generations unlike any other field. Raise your hand if you, at some point in your life, ever wanted to be an astronaut. See? Space exploration is inspiring and it's intriguing. And even for the majority who don't end up actually becoming astronauts, like this guy, just that seed of inspiration that is sometimes planted at a young age can change that person's perspective on their own education. That seed of inspiration might get them more interested in math or science or engineering. Another wonderful benefit of space exploration is hope. Hope for the future. We could actually outlive this planet someday. But space exploration gives us real hope based on real science and not just science fiction, that we might be able to colonize outer space and even other planets someday. The great Russian and Soviet rocket scientist Konstantin Tchaikovsky, who was a founding father of rocketry and astronautics, said it this way. He said, "Earth is the cradle of humanity, but one cannot live in the cradle forever." So there you have a handful of benefits and arguments for exploring outer space, asteroids, and other planets. But to be fair, it is not going to be easy. We've faced danger and death in our efforts to conquer the frontier of space travel. Just like the early American pioneers and explorers faced danger and death in their efforts to conquer their frontier of westward expansion. This is the Apollo 1 crew, Gus Grissom, Ed White, and Roger Chaffee. The Apollo 1 mission was planned to be the first manned mission of the Apollo moon landing program. But this mission never left the ground. A fire broke out inside the spacecraft during a launch dress rehearsal on the ground on February 21st, 1967. All three astronauts were killed in the accident before rescue crews could get to them. This is the crew of Space Shuttle Challenger, mission STS-51L. They were all killed on January 28, 1986, when their rocket's fuel tank exploded during liftoff and the Challenger spacecraft broke apart and fell to Earth. About 1/6 of the American public witnessed this terrible disaster live on television, mostly because of the presence of payload specialist Krista McAuliffe. That's Krista in the top row, second from left. She was a high school social studies teacher from New Hampshire. She would have been the first teacher in space. And this is the crew of Space Shuttle Columbia, mission STS-107. This crew completed a very successful mission in low Earth orbit, but they were all killed during re-entry on February 1st, 2003, when the Columbia spacecraft broke apart and fell to Earth. The damage to Columbia that caused the accident actually occurred during liftoff when a large piece of foam insulation broke away from the fuel tank and struck Columbia's wing at high velocity. Obviously, space exploration is risky and it is fraught with danger. But we keep exploring, even though we know it's dangerous. We keep exploring because it's important. It is worth doing. The payoff is really great. If these heroes could speak to us today, I think they would tell us to continue to explore. Now, going back to the American pioneers and their logistics problems, just like they had to live off the land and use local resources in order to survive, we're going to have to live off the land, so to speak, in our efforts to conquer the frontier of space travel. Exploration for more than just a couple of days outside low Earth orbit won't be possible otherwise. These pioneers actually had it easy when you think of it. They didn't have to lug along all of their breathing air and drinking water because it was all around them. In the context of space exploration, living off the land is known as in situ resource utilization, or ISRU. In situ is Latin for on site. So it's actually on site resource utilization, or using the resources that you can find on site. ISRU is pretty exciting because it's a way to reduce the mass and the cost of space exploration. You might be surprised to hear that there are quite a lot of resources out there. The Earth's moon, for example, it may look like a dry, useless rock, but it's not. NASA has proven that there's water ice located in permanently shadowed regions of the moon. And scientists believe there's even more water ice under the surface hiding from our instruments. So what will we do with the water ice? Well, we could make water, and that's pretty useful, at least for us humans. But since water is actually H2O, we can split the water molecules into hydrogen and oxygen, which are both very useful resources. Those just happen to be the ingredients for a very highly efficient rocket fuel, which means we could actually make rocket fuel on the surface of the moon someday. And this seemingly useless rock and dust that makes up the surface of the moon is actually very useful. The rock and dust on the moon, commonly referred to by scientists as regolith, is made up of minerals and compounds that consist of more than 40% oxygen atoms by weight. And since we breathe oxygen, that's obviously a super useful resource. Lunar soil, or regolith, also contains lots of other useful raw materials like silicon, iron, aluminum, and magnesium. We could actually make some pretty useful things out of all those raw materials. Now let's turn our attention to Mars. What precious resources might be there on Mars? We'll start with the Martian atmosphere, which is mostly carbon dioxide. A full 96% of the atmosphere on Mars is CO2. Each molecule of carbon dioxide is made up of one carbon atom and two oxygen atoms. And we've already talked about how useful oxygen is, but carbon actually has lots of uses. Carbon is the basis for composite materials, which are very strong and also very lightweight. And carbon can also be used in on-site 3D printing. We looked at the composition of lunar soil a few slides ago, and Martian soil is very similar, at least the volcanic portion of it is. These are basically the same elements that we've found in lunar soil, but they're just distributed differently in various minerals and compounds on Mars. Martian soil consists of a little less than 40% oxygen atoms by weight, and it contains a lot of iron, which is what tends to give the soil its reddish color. But what precious resources are lurking just below the surface on Mars? In 2001, NASA's Mars Odyssey probe scanned the red planet from orbit and found plenty of evidence for water ice just beneath the surface and all over the planet. Even the equatorial regions, which are the warmest regions of the planet, appear to contain a significant amount of precious water ice, which can be turned into water or breathing air or rocket fuel. Towards the polar regions, where the temperatures are colder, NASA has photographed huge sheets of dry ice or frozen carbon dioxide. These huge sheets of dry ice grow and recede as the seasons change on Mars. So there are definitely lots of different types of precious resources outside of our planet Earth that we might be able to use as part of our exploration missions. And it's just not going to be an option for us. ISRU technologies are going to be needed for missions where astronauts will live, work, and be productive on another planet. There's just no way economically that we'll be able to pull off those missions without living off the land. Let's consider the Apollo moon program. All of the Apollo moon missions were basically short camping trips for our astronauts. We launched those missions carrying everything we needed for the trip there, which took 3 days, and for their stay on the surface, which was from a few days to a week, and also for their return home, which was 3 more days. After Apollo, the scientific and engineering community started thinking about possible future long-duration missions to other destinations, like Mars, for example. And they thought about what would be required to live and work long-term on another planetary body. And so they performed detailed calculations, and they ran computer simulations, and they came to a surprising conclusion that they would need to set off from the surface of Earth with about 226 kilograms of fuel in order to get just 1 single kilogram of fuel landed safely onto the surface of Mars. Most of the other 225 kilograms of fuel would be used up just getting that single kilogram of fuel first into low orbit. And then some more fuel would be used getting out of low Earth orbit and into a path toward Mars. And then more fuel is used getting into a Mars orbit, and then more is used getting your craft slowed down and finally safely landed on the surface of Mars. So if we wanted to get, say, 1 ton of fuel from Earth to the surface of Mars, just multiply that 1 ton by 226. You'll have to launch 226 tons from Earth just to get 1 ton landed safely on Mars. Things get really unreasonable really quickly. So this is the technical reason why ISRU technologies are required for missions where astronauts will live, work, and be productive for long periods of time on another planet. There's just no way we could launch and haul all the resources that would be required otherwise. Now that math isn't quite that extreme for long duration missions to the moon, but the more that we're able to live off the land, the longer our lunar missions can last before they require logistics trips from Earth. And this is why NASA and the entire space industry is starting to focus heavily on ISRU technologies and ISRU experiments and ISRU missions. Earlier, we looked at lots of various reasons for exploring and colonizing Mars. But NASA has created the following short video with a little help from Hollywood that speaks to the heart of why we explore. Hopefully the audio will come through on this video.
Roger the pitch. 7. 5. Roger, Roger. You're looking good.
3, 2. We are the explorers. We have a need to find what is out there. It is a drive inside each and every one of us. The drive to wonder, to push the boundaries, and to explore. We expanded across our lands, settling new frontiers. We took to the oceans and learned that we could cross treacherous expanses in the pursuit of discovery. And then we took to the skies and flew. But that wasn't enough. We left the planet and redefined what was possible. We flew in space. We walked in space. What once was a melodramatic flight of fantasy became reality. Then a new generation of spaceships captured hearts and minds for 3 decades and helped build a castle in the sky that is our lasting home in space. We have always looked up. For centuries, we wondered what was on the other side of the sky, and we have begun to answer that question. We have learned that all the exploration humankind has achieved is only a beginning. Right now, men and women are working on the next steps to go farther than we have ever gone before. New vessels will carry us, and new destinations await us. Everything we have ever accomplished leads to this moment in time, where exploration will now take us to the planets and the stars. Our nearest neighbors in the night sky have beckoned us, invited us, dared us to reach for them. We are the explorers. Throughout our history, we have taken both small steps and giant leaps in that pursuit. Our next destination awaits. We don't know what new discoveries lie ahead, but this is the very reason we must go.
So my message for you here today is that we all are the explorers and the pioneers, not just the NASA astronauts or the NASA workforce or the aerospace contractor employees, not even the entire American population. Sending humans to Mars to explore and to set up residence, even a temporary 1-year residence, is an earthling effort. It's a humankind effort, and it'll be a humankind accomplishment. And we will all take pride in that accomplishment when it's completed. So when you go back to work next week and you're sitting in that cubicle or that office or that classroom, instead of focusing on doing great work for your boss, focus on doing great work for your boss and for humankind. Because it doesn't matter whether you work in the engineering field or the medical field or human resources or business management or education. Your work in that office is part of a much larger picture. I don't know exactly where your work is going to take humankind, but I, for one, am excited to find out. So get out there and try to do great things, even though there are probably dangers out there, because explorers take risks and explorers face dangers because it's worth it. The payoff is great. So remember, we are the explorers. And like the video said, we aren't sure exactly what new discoveries lie ahead, but that is the very reason we must go. Thank you. And it looks like we have just a few minutes for questions if anyone has any questions. My name is Kurt Lloyd, and I work in a group here at NASA called SwampWorks. And our goal in SwampWorks is to develop and advance technologies that are going to be needed for working and living on the surfaces of the moon, of planets, and of other bodies in our solar system. SwampWorks is a lean and agile development environment. We pride ourselves on being rapid, innovative, and cost-effective. We start small and cheap, and we iterate and build up quickly. We use a hands-on approach. We prototype and test early and often, and we learn fast. You're probably familiar with the famous Apollo 13 quote, "Failure is not an option." Well, in SwampWorks, failures are allowed, even encouraged, because failures in the early idea prototyping phase drives out issues quickly and forces design improvements quickly. We believe it's better to try out lots of different ideas quickly, even if some of them don't actually work out, rather than go too far down a road of design and development for an idea just to find out later, after expending lots of time and lots of effort, that it's just not going to work. Many of the technologies we're working on in SwampWorks are focused on living off the land, on the moon, or on Mars, and using the local resources that we can find there. And you already know that NASA has found evidence of frozen water on both the moon and on Mars. The Lunar Prospector operated in lunar orbit in 1998 and 1999, and one of its instruments remotely measured hydrogen on the surface, which could be an indication of water molecules. These measurements that were taken from orbit showed that there might be frozen water sitting in the coldest parts of the moon, sitting inside deep craters, both at the north and south poles of the moon. But we needed better evidence than that. So in 2009, we sent the Lunar Crater Observation and Sensing Satellite, or LCROSS, on a sacrificial flight to the moon. LCROSS actually tossed its own rocket stage so that that stage would crash into the bottom of a crater at the south pole of the moon. Then LCROSS sacrificially followed closely behind, sensing the molecules that were lofted above the moon's surface, all the while sending a live stream of data back to Earth right before it itself also crashed into the moon. And I may have lost, there we go. This mission, it was risky, but it paid off big time. The data that was streamed back to Earth did in fact show that water was there. But why do scientists care whether there's water on the moon? Well, if it's there and in significant quantities, we can use the water. It's what we call a precious resource. Water on the moon is sort of like gold here on Earth. It's hard to find, and it's worth a lot. If we can get our hands on water on the moon, it'll allow us to send our human explorers to live and work there for long duration missions. And we won't have to ship tons of water or oxygen from Earth, which we've already gone over. Now, NASA has been working on several robotic technologies that might be able to find and collect water on the moon and turn that water into other useful resources like breathing air or rocket fuel. So let's explore these robotic technologies. First, we'll need to find or locate the water. One way to look for water is to send out a roving search vehicle. This rover, which you actually saw earlier in an earlier presentation, is designed to dig up a core sample from 1 meter below the surface and to test and see if there's any water in that sample. And NASA plans to send a rover similar to this one to the moon in order to verify for sure using hands-on equipment rather than just remote sensing to verify that for sure there's definitely water there and to see how deep the water is beneath the surface. But what if a wheeled rover like this can't actually get to the water? What if the water is down at the bottom of a very deep and steep-walled crater? What if the water is inside a cave? Well, in that case, one solution would be to use a flying robot rather than a driving robot. This is a design for a flying robot that uses compressed gas thrusters rather than propellers to fly around in space or on another planet or on the moon. It's basically a thruster-powered quadcopter or drone. This robot is out to prove that we can prospect or search for water in very hard-to-reach areas, like asteroids, or even inside caves. Caves, you say? On the moon, you ask? Yes. This is a photo that was taken from lunar orbit, and it clearly shows a lava tube on the moon. And lava tubes are caves that were formed long ago by lava flow near the surface of the moon. In this photo, you can see a chain of collapsed sections, and it transitions to a continuous uncollapsed area towards the bottom of the photo. This particular tube shown in this photo is about 50 kilometers long. And this photo kind of points out the dangers of exploring inside lava tubes. They can collapse on top of you. So exploring them would best be accomplished with unmanned and fully autonomous robots. Here's a close-up photo of a lava tube ceiling collapse on the moon, which was taken from orbit. Wouldn't it be cool to explore this underground cave on the moon? There might be frozen water down there that never sees any sunlight. And lava tubes can be found on Mars, too. This photo of the surface of Mars was also taken from orbit. And at first glance, it looks like any other crater on Mars. But in the middle, you can clearly see a dark shadow, and the incoming sunlight is actually shining on a surface down below. To give you a feel for scale, the hole is about 35 meters across. Scientists believe that the larger crater-looking formation isn't an impact crater, but was actually formed over time as the rock and dust fell into the hole, sort of like a sinkhole or an hourglass effect. This computer-generated graphic shows what it might look like for this flying robot to explore an underground cave on Mars. Pretty cool, huh? It's like a science fiction movie. Now, wheeled rovers and flying robots are two possible ways to look for water on the moon or on Mars. But what if the water we're looking for is just spread out over a very large area? One or two robots just isn't going to be very efficient at searching a very large area. So what is efficient at searching a very large area? It turns out that ant colonies are. At least for their size and for their brain capacity, ants are quite good at searching an area, finding food and water, and bringing those resources back home. And ants accomplish all of these tasks without any real leadership or direction, and without a map of any kind. And so we've programmed ant behaviors into a group of small robots. We call them the swarmies. The swarmies are able to find and collect simulated water from an unknown area that is filled with obstacles. The robots use simulated chemical trails to communicate with the other robots. It's difficult to manually control a large swarm of robots. And so this system is designed to be fully autonomous and require no operator inputs once started. Now, once you're done finding the water, your task switches to collecting or gathering the water. So we'll need to dig up the dirt using some mining equipment. Here on Earth, when we excavate or mine, we use heavy digging equipment like this. But heavy equipment like this doesn't really work very well in space. Every pound, every ounce even that we launch into space is precious and very costly. And so we've been researching ways to dig or excavate using very lightweight equipment. We call this robot Razor. It's not very big. It's only about the size of a go-kart. But Razor is designed specifically to dig and to do it in less gravity than we have here on Earth. Razor digs using large rotating bucket drums and small digging scoops on those drums. The bucket drums are hollow inside in order to store the excavated material, and the drums are just rotated in the opposite direction to dump out the material. In this animation, it is showing Razor operating on Mars. There are lots of innovations in this robot's design, but probably the biggest and most impactful innovation is the counter-rotating drum system. While digging, the drums are rotating in opposite directions, and that opposite rotation actually makes the horizontal digging forces actually cancel each other out. What this means is when the robot is digging, it can barely even feel any resistance from those digging forces. And it doesn't need to provide a lot of wheel traction in the opposite direction like the heavy mining machines we use here on Earth. By testing this excavation design in the lab and by lifting up on the robot, we've proven that this robot can dig in very low gravity conditions. And that is going to be very useful on the moon or on Mars someday. We talked about the swarmies earlier for finding resources, but I think a swarm of robots might be helpful for gathering resources too. If we used a small swarm of Razor excavators rather than just one, we might be able to keep a constant stream of raw materials flowing into the processing plant. Okay, so we have located the water, and we've gathered and collected piles and piles of soil, which may or may not contain water or ice inside. So now we have to get the water out of that soil. We're going to need some sort of processing plant on site to extract water from the soil. This is an artist concept of an automated soil processing plant on the moon. This drawing shows an older version of our Razor excavator robot bringing soil to the processing plant. The processing plant can pull the water from the soil, and using the magic of chemistry, it can turn those water molecules into more useful things like breathing air or rocket fuel. And many parts and components of a future lunar soil processing plant have been proven at a small scale in the lab. But these parts and components still require more development and more testing here on Earth before they could ever get turned into a real flight system that we can launch to the surface of the moon. Those were just a few of the ways that we can find, collect, and process water on the moon. But we also might be able to use the soil on the moon for construction projects. As mentioned earlier, in situ means on site. So here are a few on-site construction ideas for the moon and for Mars that NASA's been working on. Most proposals for building outposts on the moon or on Mars involve sending prefabricated modules all the way from Earth and putting them together on site. There are some limitations to this kind of thinking because everything we ship from Earth is very costly. Also, everything we ship from Earth is limited in size. ISRU researchers are thinking outside the box, though. We're now looking into the possibility of sending construction equipment to the moon or to Mars to build roads or landing pads or even large structures right there on site. One technology area being explored is 3D printing with moon dirt. And moon dirt is basically just crushed volcanic rock. And as mentioned earlier, scientists call the crushed volcanic rock regolith. You might be familiar with common everyday office 3D printers. They melt plastic and they squeeze it out a small nozzle. It's kind of like squeezing toothpaste out of its tube, but at a much smaller scale. These 3D printers, they squeeze out layer after layer of thin plastic to build up complex three-dimensional parts. It's pretty amazing technology. And NASA researchers are looking into the possibility of 3D printing on a large scale using molten regolith. Laboratory testing has shown that in compression, regolith is stronger than typical building grade concrete here on Earth. That may seem surprising, but regolith, as I mentioned, is basically just rock, and it is quite strong. We have had some success in the lab, as you can see from this video, especially when we add a binder material to the crushed volcanic rock. But our goal is to eventually print using only rock and not have to add any sort of binder material to the mix. This is because we want to eventually 3D print freestanding structures on the surface of the moon and eventually on Mars too. Like protective garages for storing future exploration rovers and equipment. And we want to use only materials that are found locally because we don't want to have to ship tons and tons of materials like special binders all the way from Earth. This on-site 3D printing technology could be used to build roads, landing pads, dust barriers, micrometeorite protection shields, garages, and pretty much any standing structure that you can think of. Another idea we're working on is the creation of tough interlocking tiles on site. The robot in this photo is placing interlocking tiles on the ground like puzzle pieces in a field demonstration that we performed in Hawaii. And we actually controlled this robot from our lab in Florida. These tiles on the ground were created completely from crushed volcanic rock using a high temperature baking technique. So what we basically did was we used their dirt and a remotely controlled robot to build a prototype landing pad, which is almost exactly what we'd like to do on the moon and on Mars someday. In addition to these technologies for living off the land, NASA is also working on the rockets and the spacecraft that will take our NASA astronauts back to the moon and eventually all the way to Mars. NASA is right now building up a very large rocket called the Space Launch System, or SLS. This large rocket will be capable of launching very heavy modules and other large payloads into Earth orbit or even to further destinations. We're making two slightly different versions of the SLS rocket, a crewed version and an uncrewed cargo version. You can see the crewed version and the cargo version of the rockets here in this graphic. And for scale comparison, you can see the Saturn V rocket that we used to go to the moon there on the far left, and also the space shuttle. The Space Launch System rockets are very, very big rockets. And these big rockets are going to help us send humans back to the moon and eventually to Mars. We're also right now building and testing a new crewed space capsule called Orion. Orion will be capable of supporting crew for long duration deep space missions. It'll be capable of supporting a crew of 6 astronauts for a trip to lunar orbit and back. And we're planning on doing that in just the next few years. Once complete, the SLS rocket and the Orion spacecraft will work together and allow us to assemble a small outpost in lunar orbit. This is a rendering of the Lunar Gateway. The Lunar Gateway is a stepping stone or a gateway between Earth and the moon. It'll allow us to build up infrastructure and capabilities that we can then send down to the lunar surface, including our next human exploration missions. Our new human exploration mission to the surface of the moon is called the Artemis program, which is fitting because in Greek mythology, Artemis was actually the twin sister of Apollo. Here's how the Artemis program will work in a nutshell. We will build the lunar gateway in lunar orbit. Then we will send a new lunar lander and we will attach it to the lunar gateway. So now both the lunar lander and the lunar gateway will be in orbit around the moon. The lunar gateway will not be occupied full time like the space station is today. Astronauts will only use it as a stopping off point for their lunar missions. Then sometime later, we will launch our astronauts inside the Orion space capsule riding on top of that big SLS rocket. They will fly their Orion space capsule all the way to the lunar gateway in lunar orbit. Then they will get inside the lunar lander. They will get inside their lunar lander, which you recall was previously attached to the lunar gateway. And they will fly that lunar lander down to the moon's surface. They will land at the south pole of the moon and explore there. We have never been to the south pole of the moon before, so this will be very exciting. This mission will send the first woman and the next man to the surface of the moon. After a few days, when they're all finished exploring, they will get back into the lunar lander and they will fly just part of it, what's called the ascent stage, back up to the lunar gateway, which is still in lunar orbit, waiting patiently for them to return. From there, they will get back into their Orion space capsule and they will fly it back to Earth and they will land in the ocean, similarly to the Apollo missions in the 70s. Now, our first mission to return humans to the moon is planned to be accomplished in the year 2024, which is only 3 years away. But because we're using technologies that we're comfortable with and familiar with, it should be doable within that time period. Our moon exploration plans do not stop there, though. This is just the very first mission that I've described to you. We want our lunar exploration program to be sustainable this time. We want to live and work on the lunar surface longer than just a few days. We want to live off the land and use the local resources that are found there. And that is going to require some new technologies that NASA is still developing and working on, like a living module called a habitat module, or HAB, and a greenhouse for growing fruits and vegetables, and new exploration vehicles for the astronauts to drive around in and explore, and new landers and ascent vehicles that actually use rocket fuel that was made locally on the surface of the moon. Then once we have a long-term and sustainable lunar exploration system in place, we can start planning and designing our human exploration missions to Mars. Those Mars missions are going to be more complex and more risky than living on the moon. But many of the technologies necessary for long-term exploration of Mars will have already been developed and used on the surface of the moon. And a lot of those technologies will translate directly to Mars missions. So those are basically NASA's long-term plans to get humans living and working on the surface of the moon and eventually on Mars. But why send humans to the moon or to Mars at all? Couldn't we just continue to send bigger and smarter unmanned robots indefinitely? Yes, we could. But we think we can learn so much more and experience so much more by sending humans to explore the moon and eventually Mars with the help of robots, rather than just sending robots by themselves. The astronauts that will live and work long-term on the surface of the moon and eventually on Mars, and also the engineers and scientists back here on Earth preparing the way and supporting those planetary explorers, are probably right now very close to the age of the students in this photo. And when I go out into communities and schools and I talk to the students and I see their excitement and I hear all the great questions that they ask me about robots and about planetary exploration, I feel good about their chances for success. I believe they're going to actually live and work long term on the surface of the moon someday and Mars. And they will continue the exploration that we've started with our unmanned robots on Mars. You know, sometimes the younger generation gets a bad rap from the older generation. But from what I can tell, the future is pretty bright.